Good morning, all. Myself is Vigneshwari from SNS College of Technology in the Department of Electronics and Communication Engineering. So, today I am going to take the topic on synchronous counter under the unit sequential circuits. So, this comes under the subject Digital Principles and Computer Organization. So first, why do we need a counter, right? So counters we need for every events which we track. Only then we can able to know how many steps have been completed. So counters are being used in our day-to-day categories also. For example, in digital clocks, in lifts, elevators, and also for industrial automation. The thing what is the limits here is humans we cannot track the events which happens in the high speed category, so here we need a counters. So counters in our daily life, where do we see counters? We see in our digital clocks, then when we are in the traffic, when we are stuck in the traffic, all the timeline it starts to track down. So what time we can start the vehicle as such. So traffic light sequencing and washing machine. So how many wash cycles have been completed or what is the total duration of the machine it takes to complete it. And also for token number system display where we can see in the pharmacy counters also even now, and the power consumption meters. So all these that include our counters in our day-to-day life. So first, counters, it is used to track the events which happen sequentially, and this can be categorized into two types. One is synchronous counter, the other one is asynchronous counter. So synchronous counter, here all the events are being triggered simultaneously, which means when we give a single clock pulse for all the flip-flops placed, right, it starts to track the events. Whereas in the case of a asynchronous counter, the flip-flop 1 will be triggered by the clock pulse, and further the flip-flops connected will be triggered upon the output of the previous flip-flop. So this where the delay occurs in the case of a asynchronous counter, since the flip-flop has to wait each and every time until the previous flip-flop produces the output. So only upon the output produced by the previous flip-flop, it will able to trigger the next flip-flop and so on. And this process continues in the case of a asynchronous counter. Whereas in the case of a synchronous counter, all the flip-flops will be triggered by the same clock pulse simultaneously, which reduces a major ripple delay occurring in the case of an asynchronous. And this synchronous counter is also very fast in calculating, which is quick and efficient counting progress happens here. What are all the types that we see in the synchronous counters are, we have up counter, we have down counter, and the combination of both, that is which it could able to count upwards and also downwards in the same design of the flip-flop. Here the flip-flops will be activated simultaneously by the only one clock pulse. So and it also produces a consistent and dependable counting performance in the case of a synchronous counters. Here no delay between the flip-flop transitions also we don't have any delay here. So synchronous up counter. What is a synchronous up counter? So we are going to count upwards. That is start from example 0, 1, 2, 3 and so on according to the modes given the design part. So it counts in the increasing binary sequence. Say for example if it is of a 3-bit counter, it starts to count from 0 to 7, which means 0, 1, 2, 3, 4, 5, 6, 7, and after 7 it comes back to 0 again. So each state it changes according to the clock pulse given. So the major advantage is here you can predict the timing. So truth table, when we are designing such counters, we are generally using a flip-flop. So here we are using SR flip-flop, which is a set reset flip-flop. In SR flip-flop, when the clock pulse is been given, it starts to change the state accordingly. So when it is 0 0, there will be no change, and when it is 1 0, that is when set is given high, it starts to set, and when it is reset is given high and set is been given 0, it holds the reset state. When both the flip-flop, when S and R, set and reset is equal to 1, that indicates an invalid condition, which is not possible in the case of an SR flip-flop. Here, all the flip-flops will be connected in parallel since it is triggered by a single clock pulse simultaneously, and the gate ensure a proper switching between the states, and this is efficient in highlight control signals also. And then we are going to design using a JK flip-flop. So if we are going to use a JK flip-flop, the invalid condition of an SR flip-flop, which is 1 and 1, here it makes as a toggle state. Toggle state, whatever the previous condition is, it starts to toggle. If it is 1, that will be 0, or if it is 0, that will be made as an 1. So that is what we say as a toggle state, and the characteristic equation is JQ bar plus K bar Q. So here each and every timing diagram will be indicated based on the output produced. So here, since we are dealing with a 3-bit starting from 0 to 7, so Q0 it toggles for every clock cycle, and Q1 will toggle for every 2 clock cycle, and Q2 will be toggling for every 4 clock cycles, and such binary sequence will be visible at the end. So how you are going to implement this? You can implement using either JK flip-flop or a T flip-flop based upon a given, right? IC 7493 or IC 74163. So how we are going to test it? So we are going to test it based on the applications either in digital clocks and watches, or frequency divider systems, or modulo and counters. So according to the design. And then in a synchronous counter, the flip-flop are triggered by the same or a common clock signal. And a modulus 8 counter, it requires how many flip-flop? Since it is a mod 8 counter 2 power n category, so here it is requires a 3 flip-flops. So thank you.